Hello, my dear students. How are you all? I am fine. I am Khandukar Fazle Rabbi, lecturer, Department of Chemistry, Milestone College, Uttara. During this pandemic situation, welcome you all to our online chemistry class. My dear students, today we discuss about some important topics from chemistry first paper, chapter 2, qualitative chemistry. My dear students, our first topic is electromagnetic spectrum. The spectrum formed by the interaction of magnetic field and electric field is known as electromagnetic spectrum. In other words, the whole spectrum obtained when different electromagnetic radiation are arranged with increasing order of wavelength or decreasing order of frequency is called electromagnetic spectrum. Electromagnetic spectrum are of two types. First one is continuous electromagnetic spectrum and discontinuous electromagnetic spectrum. So let's we discuss about continuous electromagnetic spectrum. When sunlight passes through a prism, the radiation is split into 7 colors. In a photographic plate, the colors are attached to each other. Rainbow formation in the sky also contains a combination of 7 colors which are continuous. The 7 colors are violet, indigo, blue, green, yellow, orange and red. Among these, violet has the smallest wavelength with highest energy. The red lines at the end of the spectrum has the largest wavelength with least energy. Molecular spectra are also continuous form of spectra. Now, discontinuous electromagnetic spectrum. Spectra obtained from an element are discontinuous. When atoms of an element are excited thermally or electrically, electrons of the atom absorb energy and are raised from lower energy orbital to higher energy orbital. When heating is stopped, the electrons return back to the previous orbitals within a very short time. For transition from lower orbital to higher orbital, the electrons absorb a certain amount of energy. When returning back to the lower energy orbital, the electrons emit the absorbed energy as radiation. The spectrum created during absorption or emission is called atomic spectrum. My dear students, atomic spectrum are of two types. First one is atomic absorption spectrum and atomic emission spectrum. Now, atomic absorption spectrum. When radiant energy from a source is passed to an atom kept in a glass tube under low pressure, the atom absorbs some of the energy. As a result, the intensity of the incident radiant energy decreases. If the decreased radiant energy is analyzed under a spectroscope, certain black lines appear at the photographic wavelength. Different black lines are known to be line spectra and is also called atomic line spectra or atomic absorption spectrum. Line spectrum shows only certain colors or specific wavelengths of light. Now, atomic emission spectra. When electric discharge is carried out to gaseous atom of an element in a glass tube at low pressure, the electrons of atom absorb some energy. After absorbing the energy, the electrons move from lower energy orbital to higher energy orbital. Within a few short time, the electrons return back to the lower energy state. The absorption energy is then emitted by the atoms as radiation. Analyzing the emitted radiation by spectroscope shows the appearance of discrete group of colored lines on the photographic plate. These colored lines are known as atomic spectra or line spectra. Line spectra are unique characteristics of elements because atom of each element possesses unique electron configuration which gives rise to characteristics line spectra. Analyzing the line spectra, it is possible to identify elements as for example, when high voltage current is passed through hydrogen gas in a glass tube at low pressure, that means 10 millimeter mercury pressure, pink colored radiation is emitted. Spectroscopic analysis of this pink colored radiation revolved into four colors, namely violet, blue, green and red. These colors are known as spectra of hydrogen. These line spectra are of definite wavelength which cannot be shown by any other element. That is why atomic spectra are the unique characteristics of element. My dear students, now we discuss about Bohr's atomic model and hydrogen atomic spectra. The explanation of hydrogen atomic spectra in one of the greatest success of Bohr's atomic model. When sufficient amount of energy is supplied to hydrogen atom, the electrons absorb a definite amount of energy and get excited. This causes a transition of electrons from lower energy level to a higher energy level. The spectra obtained due to absorption of energy is known as absorption spectrum. Within a very short period of time, electrons emit radiations of definite wavelengths and return back to the lower energy states. The spectrum obtained due to emission of radiation is called emission spectrum. When an electric current is passed through a glass tube that contains hydrogen gas at low pressure, hydrogen atom get excited and emit radiant energy. When this light is passed through a prism, narrow bands of line spectra are observed. These line spectra are not continuous like white light created spectra. The narrow bands consist of several parallel spectral lines and are separated from each other by dark background. The visible part of the line spectra can be observed by naked eyes. In 1885, scientist Balmer discovered the visible lines of the hydrogen spectrum. These are called Balmer series. Balmer found four narrow lines: red, bluish green, blue and violet, which are known to be H alpha, H beta, H gamma and H delta line respectively. These are present in the visible region of electromagnetic spectrum. Balmer showed that the wave number of each spectral line can be expressed as nu bar equal to RH 1 by n1 square minus 1 by n2 square. In this equation, RH equal to Rydberg constant and n1 equal to 2 and n2 equal to 3, 4, 5, 6, etc. After Balmer, other scientists discovered 5 more series of spectral lines in the whole atomic spectra of hydrogen using higher resolution spectroscope. These scientists obtained these spectra by exciting the electrons at different energy levels. The series are: first one, Lyman series. If n1 equal to 1 and n2 equal to 2, 3, 4, 5, 6, etc., then the promoted electron returns back from higher energy level n2 equal to 2, 3, 4, 5, 6, etc. to lower energy level n1. The spectral lines obtained from electron transition between n2 to n1 are called Lyman series. So we can say that for Lyman series, n1 equal to 1 and n2 equal to 2, 3, 4, 5, 6, etc. Second series is Balmer series. For Balmer series, n1 equal to 2 and n2 equal to 3, 4, 5, 6, etc. Then the excited electron returns back from higher energy level to lower energy level n1 equal to 2. The spectral lines obtained from this electron transition give rise to 4 line spectra. These are called Balmer series after the name of scientist Balmer. These lines are all in the visible region. Now, Peschain series. Peschain series of line spectra are due to electronic transition from n2 equal to 4, 5, 6, etc. energy level to n1 equal to 3 energy level. In 1908, scientist Peschain discovered this series. These spectral lines appear at the infrared region. My dear students, fourth series is bracket series. If n1 equal to 4 and n2 equal to 5, 6, 7, etc., the promoted electrons return back to lower energy level. That means the electrons return back from 5, 6, 7, etc. energy level to fourth energy level and give rise to spectral line. This bracket series line in the infrared region. And the last series is Fund series. When the excited electrons return back from energy level n2 equal to 6, 7, 8 to energy level n1 equal to 5, then the series of spectral lines are observed. In 1924, Hermann Fund discovered the series. These spectral lines appear at infrared region. Now I discuss with you some mathematical problem from these topics. Okay. To solve the mathematical problem, we need some formula, and the formulas are here. Here nu bar equal to RH 1 by n1 square minus 1 by n2 square, Here nu bar is the wave number, and RH Rydberg constant, and the value of Rydberg constant is 109678 centimeter inverse 1, and we can also write 1.09678 into 10 to the power 7 meter inverse 1, and N1 and N2. Here N1 and N2 is energy level, where N1 is less than N2, and 1 by less, our second formula, 1 by lambda equal to RH 1 by N1 square minus 1 by N2 square, and nu, this is nu equal to frequency. We know that nu equal to frequency, and nu equal to CRH 1 by N1 square minus 1 by N2 square, and another formula is E equal to H nu, and E equal to mc square. Here we use H is Planck's constant, and we also use here C equal to 3 into 10 to the 8 meter per second, and we can also write 3 into 10 to the power 10 centimeter per second. My dear students, now we solve this mathematical problem. Here we see that here shell number 1, 2, 3, 4, and this electron shifts from shell number 4 to shell number 2. And our question is, what will be the wave number, wavelength, frequency, energy, and color of the radiation for the mentioned shifting of electron? My dear students, we know that to calculate wave number, the formula is wave number, the formula is nu bar equal to RH 1 by N1 square minus 1 by N2 square. Here we see that the electron shifts from shell number 4 to shell number 2. So we can write here N1 equal to 2 and N2 equal to 4. So my dear students, we calculate nu bar or the value of RH equal to 109678 centimeter inverse 1. So we write here 109678 1 by 2 square minus 1 by 4 square, and we get the value is centimeter. That means the value is 20,564.625 centimeter inverse 1. This is the wave number for this transition. And now we calculate the wavelength of this transition. My dear students, we know the formula to calculate the wavelength is 1 by lambda equal to RH 1 by N1 square minus 1 by N2 square. So 1 by lambda equal to RH 1 by 2 square minus 1 by 4 square, or 1 by lambda equal to 109678 1 by 2 square minus 1 by 4 square, and we get the value is 1 by lambda equal to 20,564.625. So lambda is 1 by 2564.625, and the value is lambda equal to 4.8627 into 10 to the power minus 5 centimeter. If we convert this value of lambda into nanometer unit, so then lambda equal to 4.8627 into 10 to the power minus 5 into 10 to the power 7 nanometer. Because, my dear students, we know that 1 centimeter equal to 10 to the power 7 nanometer. 1 centimeter equal to 10 to the power 7 nanometer. So lambda is 486.27 nanometer. And our another question is the color of the radiation for the mentioned shifting of electron. We know that if the wavelength is 450 to 500 nanometer, then the color is blue. So we can write the color of the transition is blue. So we can say that the color of the transition is blue. Okay, my dear students, now we calculate the frequency of the transition. So my dear students, we know that frequency nu equal to CRH 1 by N1 square minus 1 by N2 square. And for this case, if we use Rydberg constant 109,678 centimeter inverse 1, then we have to write C equal to 3 into 10 to the power 10 centimeter per second. Okay, my dear students. Now C equal to 3 into 10 to the power 10 into 109,678, and the value of n equal to 2, so we write here 1 by 2 square minus the value of n2 equal to 4, so we write here 1 by 4 square, and the value is 6.16 into 10 to the power 14. This is hertz. Unit is hertz. So we can say that the frequency of this transition is 6.16 into 10 to the power 14 hertz. My dear students, now we calculate the energy for this transition. We know that E equal to h nu. And here h is the Planck's constant, and we get the value of Planck's constant is 6.626 into 10 to the power minus 34 joule second. And in our previous mathematical problem, we get the value of nu. So we write here the value of h equal to 6.626 into 10 to the power minus 34 into frequency 6.16 into 10 to the power 14. So we get the value 4.08 into 10 to the power minus 19 joule. So we can say that the energy for the transition is 4.08 into 10 to the power minus 19 joule.